Hello and welcome again. We will start today with our first lecture, that is the introduction to quantum computing. Let us start by defining what is computing and how we have reached to quantum computing. Well, computing in its essence involves solving problems by performing mathematical operations. You have a problem, you have some information available to you, and you apply some operation and solve that problem, and that is computing, right? This fundamental activity is everywhere, from calculating your expenses or searching any information online or even playing video game. Computing is everywhere. Let us think a little bit broader. Consider your own brain, nature's most sophisticated computer. Whether you are multiplying numbers, or you are deciding the best route home, or you are planning your day, you are actually engaging in complex calculation using your brain. Your brain continuously processes vast amount of data to help you navigate or make decisions and learn from environment. From ancient civilization to the most modern computers, computing has always been about solving problems and making our life more and more easier. Our story of computing begins in the most natural way possible, using our own hands. Early humans used their fingers to count and perform some basic calculations. As civilization advanced, so did the complexity of problems we wanted to solve, and this need led to the invention of abacus around 2400 BCE. This device dramatically improved the speed and accuracy of calculation by allowing users to represent numbers physically and perform some very basic mathematical operation. Then in 17th century, a notable advancement was made with the development of mechanical calculators. These devices could perform basic arithmetic operation. The most ambitious of these early mechanical computers was Charles Babbage's analytical engine in 19th century, which actually laid the groundwork for modern computers. The 20th century brought about revolutionary changes with the development of electronic computers. These began with massive room-sized machines that used a vacuum tube to process information. Among these, the most notable one was ENIAC, which was developed in 1940s, and it could perform thousands of calculations per second. Then in 1947, there comes a turning point with the invention of transistors. Transistors actually replaced vacuum tubes, leading to computers that were more reliable, smaller, and less energy consuming. In 1953, IBM introduced its first mass-produced computer, IBM 650, making digital computing accessible to a wider range of businesses and universities. Then again in 1950, there come a turning point with the invention of integrated circuits. These circuits allowed thousands of transistors to be embedded in a single chip, which drastically reduced the size and cost of computer. In 1981, IBM introduced its first personal computer, a computer that brought digital technology to the home and office. This was indeed a pivotal moment in computing, as it standardized the architecture for future personal computer and made computing accessible to the general public. Today, we stand in an era which is dominated by supercomputers, a machine which is capable of processing quintillion. By quintillion, we mean 10 to the power 18 calculations per second. Imagine. These supercomputers use parallel processing, where many calculations are carried out simultaneously rather than sequentially. These supercomputers today are used to perform a range of complex tasks like predicting weather or making financial models or simulating some material to analyze its behavior. So, if we have all this computing power available to us today, why would we even need a quantum computer? Well, problems are getting more and more complex with time, and here even supercomputers struggles to keep up. And this is where quantum computer steps in and set to transform computation like never before. Classical computers have certain limitations that limit its further improvisation, like the shrinking limit of classical computers. As you have seen in previous slide, with time computer has transformed from room filling devices to very sleek and handy laptops which we have today in our hand. But its further miniaturization is limited in a certain way. Why? Because classical computer use transistors as their basic unit of computation, the tiny switches that process information. The size of these transistors have been persistently reduced. Today, a commercial transistor measure just 5 nanometer across. Imagine 5 nanometer transistors we have available with us, while a research prototype is even smaller with 1 or 2 nanometer in size. These transistors are made using a single carbon nanotube or mono disulfide layers and bringing us to the edge of atomic scale engineering. But here is a catch. At such microscopic scale, the laws of classical physics start to break down and quantum effects start becoming significant, and that is the major challenge with classical computers. At the small scale, quantum tunneling and electron leakage become more pronounced. What we mean by quantum tunneling, it is a process where electron encounters energy barrier which it cannot cross classically because its energy is lower than that of the energy barrier. But in quantum mechanics, with some probability, electron can pass through the barrier and reach the other side even with the lower energy. What we understand by this in terms of electronics, well, quantum works on gates which have on and off state. In on state, an electron crosses the gate and passes the current, while in off state it cannot cross the gate and unable to pass current to the other side of the gate. By quantum tunneling, electron can leak through gate even when they are supposed to be in off state. It will cause error, power dissipation, and ultimately it is a roadblock to further miniaturization. On the other hand, quantum computer indeed uses this quantum effect intentionally to perform calculations faster. Then we have issue of energy consumption and heat generation. The more transistors we pack onto a single chip, the more power they consume and the more heat they generate. This excessive heat can limit the processing speed and reduce the efficiency. Also, increased power demand require more energy and that will contribute to the higher carbon footprint. Also, we would need advanced cooling system adding complexity and cost to computing infrastructure. Then we have some problems that are way too complex for a classical computer to solve efficiently, like encryption algorithms or advanced optimization problem. Solving them require testing millions or even trillions of possibilities, and even the world's fastest supercomputer would take an impractically long time to compute solution. Although modern computer uses multi-core processor and parallel computing, but there is a limit on how many operations they can proceed simultaneously. Classical computer execute information in a step-by-step manner, and even with optimized architecture, some problems require a truly massive parallelism, something a quantum computer can achieve naturally through superposition and entanglement. So quantum computing is the solution to these problems.